All right, we're going to start with matrices. Matrices are rectangular arrays of numbers. Um, so for instance, um, 3, 7, 1 to negative 4, 6. So that is a rectangular array of numbers. There are 2 rows and 3 columns, 1, 2, 3 columns. The notation we use is typically a square bracket, but I don't really care whether it is square or not. So in my view, this is exactly the same thing as 3, 7, 1, 2, negative 4, 6. So we do use some kind of uh, grouping symbol. Typically, most people, I would say, use the square bracket, but a lot of people also use the round parenthesis. And the size or the dimension of the matrix is always given by first providing the number of rows and then the number of columns. So the size of this is the same matrix. That's why I put an equal in between. There is the same thing. And the size is 2 by 3, not 3 by 2. Yeah, so again, the first number always indicates the number of rows, number of rows, while the second number always indicates the number of columns, number of columns. And we always have rows and columns. Otherwise, we do not have a rectangular array of numbers. That's what a matrix is. A matrix is a rectangular array of numbers. Rectangular meaning we have rows and corresponding columns. If we have an array of numbers, say you have 3, 7, 1, 2, negative 4, and nothing else, that's not a matrix. It doesn't matter what you put around it. This is not a matrix because it's not rectangular. It has some kind of, if you start, it's missing a corner in order to be a rectangular. Or if we were missing this guy, so let's say you have 3, 7, 1, 2, 6, like that. With this part missing, it's not that it has to be negative 4. It is just missing something. That is not a matrix. So a matrix has to have a number of rows. It could be as few as 1 row, or it could be 30 rows or 100 rows, and a number of columns. It can be as few as 1 column or 1,000 columns. It doesn't matter. A lot of the matrices we're going to work on are going to be about 2 by 2 or 3 by 4, that kind of thing. The numbers, the number of rows and the number of columns is going to be relatively small, and by that what I mean in this case is usually less than 5 the most. You can enter a matrix in a graphing calculator. Let's see. Here are the matrices, and so there are the names. You can edit a matrix, so you can just, I think there's one here, a big one. Yeah, there it is. So that is a matrix that is already in my calculator. The rows and the columns. So you can do a lot of math with calculators. The expectation, however, is that you will do everything by hand. That is the expectation in this video, that all the computations are going to be done by hand. By hand, what I mean by that is that we're not going to use a calculator that is more complicated than this one. This is the most complicated calculator we want to use. Now, having said that, if you finish a computation of matrices and you want to double check the answer, yes, go ahead by all means and use a graphing calculator, but don't rely on the graphing calculator to do the work for you. We want to actually do the work ourselves, and then we can double check with a graphing calculator. Otherwise, we are defeating the purpose of this mathematics that we are learning, understanding the mathematics that we are doing. And there's a lot of things we can do with matrices. Um, right now, I just wanted to introduce the concept of a matrix. And again, we can have a very, very large matrix, or we can have a very small matrix. I suppose the smallest one we could have is a 1-by-1 matrix, just with a number 3, for instance. So this is a 1-by-1 matrix. Um, we typically don't study those by themselves because they are equivalent to just regular numbers. The smallest one I suppose we have of some value are matrices that are that have 2 coordinates or 2 entries. So either 2-by-1 or 1-by-2. Oh, by the way, a point can be thought of as a matrix. So if you put 3, 2, that's a matrix that is 1-by-2, 1 row, 2 columns. Or sometimes we put commas between the numbers, sometimes we don't, as long as it is clear that we have 2 entries. So this is not the number 32, then we may or may not put commas. That depends on the teacher also. So points are the same thing as matrices. In fact, matrices that have exactly 1 column or 1 row have a special name. They're called vectors. So vectors are a subset of matrices. So these are vectors. This is a column vector, and this is a row vector. Column vector, and this is a row vector. And they are both matrices. So we got the set of matrices, big set of matrices. And inside of that, we have the set of vectors. Vectors in Rn. That's a different story. But what I mean by that is the pairs or triples or 4 tuples. There are many definitions of vectors depending on the context in which we're studying vectors. If we are studying vector spaces in general, then that doesn't necessarily fit inside of the matrices, although somebody could argue, well, they kind of do. Anyway, in a certain way, they kind of do. But let's focus just on this kind of matrices. So a special kind of matrix is what we're going to call vectors. So the vectors themselves may be called vectors or matrices. This particular one, or actually this one, could also be, either one of those two could be called points, because that is 3 units to the right and 2 units up, and there is the point. So that can be located on the XY axis. And then you may be thinking, oh, so that can be a 6-dimensional point. In a way, kinda, yeah. All right, but now let's go to the systems of equations. Oh, I didn't mention that here, but the Gauss-Jordan elimination is applied to matrices, and in turn, those matrices can be applied to solving systems of equations. Okay, so let's view an example of a system of equations, and we're going to tie the concept of system of equations with matrices. So let's label this as example 1. 2x plus 3y equals 28, and 3x plus 4y equals 39. Okay, and we want to solve this system of equations. We did this in the previous video, in which we were eliminating variables. Now, in a lot of those computations, we were quite consistent. The x's and the y's were always in the same place. and the constants were always in the same position, the same relative position, and we were eliminating by adding and subtracting and moving the equations one above the other. Um, if we keep the x's and the y's consistent, and also the constants that have no x's and no y's in the same spot, perhaps we don't necessarily have to write the extra symbols of x and the plus and the equal and the y, and we can obtain the essence of this system by just writing down the numbers, the coefficients and the constants. So to this system, uh, this system corresponds with a matrix, which we're going to call the augmented matrix for this system. So we're going to put the coefficients of the variables 2, 3, and the constant 28, 2, 3, 28, 3, 4, 39, 3, 4, 39. Sometimes we put either a solid line or a dotted line here, indicating that those are the constants and those numbers correspond to the variables. And then we close this. By the way, this is a 2 by 3 matrix. So the size of this matrix is 2 by 3. And this matrix is called the augmented matrix corresponding to the system of equations. And then we can manipulate the numbers as opposed to manipulating the whole equation with all the x's and all the y's and so forth. This can save us a little bit of work and writing if we do this carefully, if we manipulate things carefully. By that, what we mean is we have to keep the columns well defined. We don't want to start moving numbers around, because then the columns indicate that we are dealing with x's or with y's or with constants with no variables in it. Now we have to have a set of operations we can apply to the rows that are equivalent to operations that we can apply to the equations. Those operations are going to be called elementary row operations. Those are very, very important. Elementary row operations. And there are 3 of them that we may apply. And as we apply those operations, the matrix, the augmented matrix we keep obtaining by applying those operations, are going to be called row equivalent. And row equivalent augmented matrices are going to correspond to equivalent systems of equations. I know that might be a lot of information to take all at once, but it is, I mean, that's the way we have to do it. We bring a new set of information, and sometimes a lot of it comes at once, because it is very difficult to just talk about one little thing without including everything that is involved. Anyway, so there are 3 row operations. One of them is we can exchange rows at any time. Yeah. So one operation is to exchange rows. We can multiply any row by any non-zero number. The number we multiply by has to be non-zero. So we may multiply any row by any non-zero number. And the third one will be that we can add to any row a multiple of any other row. We may, I'm not being consistent because I didn't put that down up here. We may exchange rows. We may multiply any row by any non-zero number. And here, either I put we may blah, blah, blah on the 3, or we don't. So I'm not being consistent, but I'm not going to erase it because I'm taping the video and it takes too long to erase. And so, but just be aware, we mean that. So we may, yep. Add a multiple, a multiple of any row to any other row. And when I say multiple, we can multiply by a negative number. So that includes the subtraction. We can add or subtract a multiple of any row to any other row. So those are the 3 elementary row operations that we can apply to this to obtain a row equivalent augmented matrix, which will correspond to an equivalent system of equations. As we go through the example, all of this will become a little more clear. So remember, this is a lot to show you in one shot, but that's the way many times it happens. When we encounter a new topic, a new concept, a lot of things come at once, but then we little by little start chewing it and digesting it until we become very familiar with it. It's like if you go to a new place and you are unfamiliar with a new place, you know, at first you're looking at everything and the place may seem overwhelming, but little by little you start recognizing the place and you start walking around and memorizing where things are, and then you become very, very comfortable and familiar with that. The same thing is happening in a work environment. You know, there's a new system, a new environment, and initially it is very overwhelming to see that. And imagine people who just lived in their work life from no computers to computers. You know, not seen a computer before and then seen a computer. That is fairly recent. For a lot of folks, that was very, very overwhelming because there was a lot of information. You know, what do you mean a computer? Anyway, so let's continue with this. Our goal for matrices like that will be to reduce them into row echelon form, or even better, row reduced echelon form. Okay, so I'm kind of in the middle of an example while I'm showing you new concepts. So please bear with us, with me, as we go through an example while we're looking at new things. Sometimes it is a good idea to actually show you the new things as we go through the example, rather than just show you the new things in the abstract. So we're going to operate this matrix. For what purpose? What is our goal? That's what I want to mention right now. So there are two goals, two possible goals. One is to obtain, okay, so we want to obtain what is called the row echelon form of a matrix, row echelon form, or even better, the row reduced echelon form. So the row echelon form is abbreviated REF. The row reduced echelon form, as you will probably be able to tell, will be RREF. Okay, so let me explain this one first. And I'm going to explain it by showing you how it looks. So if we have a 2 by 3 scenario, a 2 by 3 matrix, so 2 by 3 case, okay, the row reduced echelon form should look like this. one, but not necessarily like this. 1, 0, number, some number, 0, 1, second number. So those numbers are not necessarily the same number, some number. So that could be the case, or there's actually a few things. Those numbers, by the way, could potentially be 0. So a number could be any number, though I'm using that symbol for any number. There's actually a couple different ways. Um, we could have 1, 0, number, 0, 0, 0. That also counts. And I believe we could have 0, 1. Actually, here it doesn't have to be 0. It can be a number, which I suppose could be reduced down to 1. Yep. Or 0, 1, 0, 0, number, and then number, which could be 1. And in fact, if we have the first element, as we read it from left to right, the first non-zero element should be a 1. So I'm going to make an arrow and point to this as a 1. That could be a 1. It should be a 1. If we really wanted to have it in row reduced echelon form. How about row echelon form? Row echelon form. It's similar to this, except that above the ones, we don't necessarily have to have 0. So 1, number, 0, 1, number. So we have numbers below the ones, if there's numbers below the ones, and to the left of the ones, if there are numbers to the left, but not necessarily above or to the right. This 1 could be here also. Yeah. Yeah. Anyway. Yeah, but anyway, I'm going to tell you what this means. This is an interesting. If you end up with a number that is not 0 here, 0, 0. So I guess it gets into two cases. For purposes of solving the system of equations, we may end up with 0, 0, 0, or 0, 0, a number that is not 0, such as 1. If you have a number if you have 0, 0, and a number that is not 0, that means that the system of equations has no solution. So please be aware of that, no solution. If we have a row of zeros, it could be that we have an infinite number of solutions. But I'm getting too deep into the things that we can end up with too soon. Let's move on to actually getting to this. So our main goal initially is to get to one of those two cases. Okay. Essentially, we want to get to this case to then later get to this case. So we get through this case first, and then we get to this case. And then there are some other cases that fall into those two categories that are a little bit weird. Those are the best case scenarios. That's what I'm trying to tell you. But let's practice so we understand what we mean by all of this. So we're going to continue example 1 still. So we have the matrix, the augmented matrix 2, 3, 28, 2, 3, 28, 3, 4, 39, 3, 4, 39. And our first goal is to have this as a 1 and this as a 0 and that as a 1. So that is the main thing. We want to have 1, 1. The method calls for dividing this by 2 right away. So we have 1, but if we divide this row by 2, we have a 1 here, which is not a problem. We have a 14 there if we divide by 2. But the problem is that we're going to end up with a fraction here. Um, and I have mixed feelings about whether to do that or not, to include fractions or not. Let's do it without fractions first, and then I'm going to do the fractions method next. So we're going to row reduce this matrix without using fractions. We're going to do the same process we did back when we were eliminating equations. I want to eliminate this 3, but I want to eliminate it with this 2, and it's kind of hard to eliminate if they don't match. So I'm going to multiply the second row by 2 and the first row by 3. Okay. Oftentimes we use an arrow indicating now we're going to have a new matrix, and we have to explain how we obtain the matrix. So we're going to multiply the first row. R1 means the first row times 3, and that means that this row is going to be 6, 9. 3 times 8 is 24. We carry 2. 3 times 2 is 6, 7, 8, 84. We multiply this row by 2 to row 2, 6, 8. 2 times 39 is 78. And then we can do row 2 minus row 1. Row 2 minus row 1. Now that means that from row 2 is going to stay as is, except that we're going to subtract row 1 to it, element by element. So 6 minus 6, 0. 8 minus 9, negative 1. 78 minus 84, negative 6. And keep the first row as is. 84, yep. All right, this is the row echelon form of this matrix. This matrix has been reduced to this. Oh, not yet. Oops, not yet. We need to divide this by 6. So divide this by 6, which is the same thing as multiplying 1/6 times row 1, and we end up with 1. 9 divided by 6 simplifies down to 3/2. 84 divided by 6, 84 divided by 6 equals 14. And we end up with 0, negative 1, negative 6. Oh, and we need to multiply this guy by negative 1. We should end up with 1s on the leading elements of each row. So the first non-zero element, as we read the row from left to right, is called the leading element, and they should be 1s. So I'm going to do that here. I'm going to multiply negative 1 times row 2. So we're doing 2 row operations. We got to be careful. As long as one doesn't interfere with the other, we are good. So now we got 1, 1 on this diagonal, and then numbers to the right or above the ones, and zeros to the left or below the ones. That means we have the row echelon form of the matrix. This is the row echelon form of the matrix. Now, let's translate this back into an equation. Remember, this is the column of the x's, this is the column of the y's, and this is the column of the constants. So what this translates into, and this is the constants in there, is that x plus 3/2 y equals 14, and y, 1y, no x, 1y is equal to 6. So we have one solution already present, and then we can back substitute into the previous equation to obtain the value of x. So we back substitute. So what is 3/2 of 6? Well, 3 times 6 is 18, but then we have to half that, so that is 9. X plus 9 equals 14, and that means that x has to be 5 to obtain x equals 5. So we have the solution 5, 6. Okay, so this is the row reduce, rather the row echelon form of this original matrix. Now, I'm not stating that those two matrices are equal, or those two, or those two. None of them are equal to any of the other. What we are stating is that they are row equivalent. This and this matrix are row equivalent, and so is this matrix, and so is this one, because we are applying row elementary or elementary row operations. So they are row equivalent. What it means, though, is that the original system that we had, which was 2x plus 3y equals 28, and 3x plus 4y equals 39, this system of equations is equivalent to this system of equations. All right, but we're not going to be happy all the time to do this. We're going to continue and reduce it even more. So we have a 0 up here. So I'm going to do that. So pretend we start out, pretend we didn't stop here and we were to continue. So start with 1, 3 over 2, 14, 0, 1, 6. And pretend we want to get rid of this guy because we want to have zeros above the 1. Not only below the 1s, but above the 1s, we want to have zeros. So what we will do is a row operation. So the row operation is to, well, multiply this row by 3/2 and then subtract this row minus this row after we multiply it by 3/2. Let me show you. Take row 1 and subtract 3/2 of row 2. I know this is a little overwhelming at first, but please, please, think of this as a new environment, a new place. It is overwhelming at first, a new method. You know, imagine how people who used to be in horses, or if they, I guess if they had the horses, they were just walking, and then all of a sudden being able to use trains and buses, and you know, it's, you know, at first things may seem very overwhelming, but after a while we get very, very comfortable and familiar with what's going on. So this is what we're doing. Multiply the elements in row 2 by 3/2 and then subtract that product from R1, the first row. So multiply this 0 by 3/2, we still get 0. 1 minus that 0, 1. Multiply this 1 by 3/2, we get 3/2. Subtract 3/2 minus 3/2, 0. And that this row operation was designed so this number goes away. By the way, when we apply row operations and we start cleaning this up, we want to go from left to right, because the zeros on these rows are not going to mess up this one. See, we want to end up with a nice diagonal 1 here. That's ideal. And if we multiply this row by a number to then add it to this row, if we did not have a 0 here, that would mess up this 1. So we have to do this carefully. You know, it's like, I guess, it's like when you are painting a floor, you don't want to paint yourself into a corner, because then how are you going to get out? You have to step on the fresh paint, which means you have to repaint again. So that's kind of what's going on here. If we don't do this carefully and put zeros first, as many zeros as possible on the first column, by the time we try to fix and put a 0 here, that's, if we don't have zeros on the first column, as many as possible, then that's going to mess up the one that we already got. Okay. And then multiply this 6 by 3/2. That is going to give us 9. 14 minus that 9 is going to be 5. And then we have 0, 1, 6. This matrix is already written in row reduced echelon form. Translating this back into an equation, what we have is that x, this is the column of the x's, x plus no y is equal to 5. No x, 1y is equal to 6. So that gives us a nice solution, if there is such a solution. Okay, again, this can be overwhelming at first, but please watch more examples, and as we go through the examples, hopefully things that are a little familiar will become more familiar and more familiar and more familiar. You know what, I'm gonna do examples, even if they involve fractions, because that's probably a good way to go about it. Okay, let me start with an easier example. I was going to do an example that is more difficult, but let's do this one. Example 2. Okay. By the way, the method all the way down to here is called Gauss-Jordan elimination. So what we did, all the steps we did through this point is called the Gauss-Jordan elimination. Gauss-Jordan elimination once we get to this point. Up to this point, when we got to the row echelon form, it is called just the Gauss elimination or Gauss method. If we get all the way down to a row reduced echelon form, then we have the Gauss-Jordan method. Okay, so second example. Let's say we have x plus y plus z equal to 9. I lied, not plus z, minus z. I don't know if this eraser works anymore, and I'm far away from the supply room, so let's just scratch it. Sorry about that. There. X plus y minus z equals 9. Gotta get a new eraser. X minus y plus z equals 11. Negative x plus y plus z equals 13. Okay, so we got a new system of equations. You know how to do this without matrices. So that is a fact. You already practiced probably a few problems and know how to handle this without matrices. What we want to do is be able to do this problem using matrices and the Gauss or Gauss-Jordan elimination method using row operations to obtain the solution. Okay, so first let's write down the augmented matrix corresponding to the system. So the augmented matrix will be 1, 1, negative 1, 1, 1, negative 1, 9. 1, negative 1, 1, 11. Negative 1, 1, 1, 13. Keep in mind, the first 3 columns correspond to x, y, z, respectively. The last column is the column of constants, corresponding to the numbers that go after the equal sign. Okay, we already have a 1 on the upper left corner. That's a good sign. This is why this problem is particularly easier than the other ones we're going to do after this problem, because we already have a 1 on the upper left corner. We want to simplify this and that number. We want to get rid of those two because we want to have zeros in this column. So we always work from left to right starting with 1 on the upper left corner, and then wiping off numbers that are below this 1. Okay. So we're going to take the second row and subtract the first row, because 1 minus this 1 is going to give us 0. We're going to eliminate the x from that equation. But this means that the first row is going to stay as is. 1, 1, negative 1, 9. 1 minus 1, 0. So we're subtracting the first row from the second row. 1 minus 1, 0. Negative 1 minus 1, negative 2. Now this is tricky. 1 minus negative 1, that means 2, because we're doing a double negative. 1 minus negative 1. 11 minus 9, 2. Might just as well get rid of this number and convert it into a 0 by adding the first row into the third row. Row 3 plus row 1. This is already 1 and this is negative 1, so we can simply add and that will turn into 0. So we do that. Negative 1 plus 1, 0. 1 plus 1, 2. 1 plus negative 1, 0. 13 plus 9, 22. Okay. So we got our first column is a nice clean column. It has a 1 on the top position, zeros underneath. Let's clear this guy up next. Because we want to end up with a diagonal of 1s if possible. Sometimes it is not possible, but that's what we want to do. We want to end up with a diagonal of 1s. You know what? If we divide this by 2, we end up with a 1 here right away, 11. And what we could do is switch those two, and that automatically, almost automatically, will give us a 1 and a 0. It is kind of desirable to do that. So please mind there are many ways to go about this. But you know what? I'm not gonna do that. Let's just divide by the second row. We're gonna multiply it by a negative 1/2. So we're going to take the second row and multiply it by negative 1/2, second row. And we're going to end up with, so that will only affect the second row. It will be 0, 1, because we're doing negative 1/2 times negative 2, positive 1. Negative 1/2 times 2, negative 1, again here. The first row is going to stay as is. The third row is going to stay as is also. 0, 2, 0, 22. Okay. So let me remind you of what's going on. Our first goal is to have a 1 on the upper left corner. We didn't have to work for that. It was already there. Our next goal is to wipe off numbers below that 1. We achieved that. So we got a nice column with 1 and zeros. Our next goal is to move on to the next element here and have, oh, actually we got that here. This element should be a 1. We want to convert that into a 1, which we did here. And now we're going to use this 1 to get rid of this 2 and the 1 above. See, we are almost immediately going into Gauss-Jordan elimination. I'm kind of skipping the Gauss part, because the Gauss part may leave this 1 there and get rid of this 2 only. But why not just get rid of the 2 of those above and below and get the Gauss-Jordan nice, clean, get down all the way down to the row reduce echelon form of the matrix, instead of kind of doing it halfway And then to do more work to achieve the other half, why don't we just do it all at once? So let's just do that. Yeah, so we're gonna skip the REF, the row echelon form, and we're gonna go directly into the row reduced echelon form of the matrix, because that's just gonna be almost as much work and might just as well do it. Okay, so we're gonna take the first row, take away the second row, and that's gonna clear this guy up. We're gonna have a 0 there. So row 1 minus row 2, let's do it, 1 minus 0, and we don't wanna mess up this 1. 1 minus 1, 0, negative 1 minus negative 1. Watch out with the negatives, because we're gonna sometimes end up with double negative. Negative 1 minus negative 1 is also 0. Here we have that again. 9 minus negative 1, that's 10. This row is good as is for now. 0, 1, negative 1, negative 1. And this row has to be fixed because we want zeros above the 1 and below this 1. And again, we want to focus on the diagonal, the first diagonal going down. So we want to have a 1, 1, hopefully a 1 here. And above and below the ones, we want to have zeros. We want to work this out from left to right. So by columns. Why do we want to do that? Because if we didn't do that, we would mess up this 1. In trying to come up with an analogy, it's kind of like, you know, you're getting all ready for a wedding or some big event like that, and you have, you know, a hairdo that is very, very sophisticated. So you go to the hairdresser and they do a hairdo, you know, and it looks gorgeous, it looks great, you know, your hair, but then you go and take a shower. So you have to kind of plan things accordingly. You know, you want to take your shower. I actually don't know too much about that. How that works. You know, my hairdo was very simple, so I didn't have to go to a hairdresser. But if I did, I don't know how I would do it. To be honest, I'm just ignorant about that. I don't know. Um, um, so yeah, but we got to do things. We don't want to do something to then in the next step mess it up. That's the message I'm trying to convey here. So that's why we want to have zeros here, because when we use one row to affect another row, these zeros are not going to mess this one anymore. All right. So we want to take care of this 2, and we're going to subtract twice this 1 to get rid of this 2. So row 3 minus twice row, oh, I meant that row 2 minus twice row 3 will get rid of this. No, I said it right. Sorry about that. Row 3 minus twice row 2. There we go. So this minus twice that. See, that's why we want to have a 0 here, because this 0 should be preserved. 0 minus twice 0, 0. 2 minus twice that, 0. 0 minus twice that, 2. That's a double negative. 22 minus twice that, 24. Okay. We got first column, second column with 1s in the main diagonal and 0s everywhere else. Now we focus on this one. So we work our way down, upper left corner, 0s. Next element in the diagonal, make it a 1, 0s above and below. That's the way we want to go about it. Then we want to focus on this guy. We want this to be a 1. So I'm going to move on to a new page. Still, we're going to do row operations. We're simply going to divide by 2, which is the same thing as multiplying by 1/2. So take the row 3 and multiply it by 1/2. The other two rows are going to remain the way they are: 1, 0, 0, 10, 0, 1, negative 1, negative 1, 0, 0, 1, 12. And some of you may be thinking, wait a minute, this means that x is equal to 10. Why don't we stop here and start back substituting into the original system and then move on? Yes, we can do that. We could do that if our goal was just to get the solution. But there's more to this goal. We want to understand how matrices can and are being reduced into row reduced echelon forms. So we're not only focusing on solving the system, because for that matter, our previous video did that. If all we wanted is just to solve a system, we don't need to introduce matrices. We want to understand about matrices. There's a lot more to matrices than just this. One of the things we need to understand is how to row reduce matrices, and that has other applications in other places. All right. So we want zeros here. We already have a 0 there, so we don't have to work for that, but we want a 0 here. So we want zeros above and below ones. Below this 1, there is zeros. Above and below this 1, there is zeros. Above this 1, there's 1 0, but we want to convert this into a 0. And ideally, we want the ones to be going down in a diagonal, like so. So the way we turn that into a 0 is by adding to R2, R3. So the first row does not change: 1, 0, 0, 10. 0 plus 0, 0. 1 plus 0, and that's why we want to have zeros here. Excuse me, because we don't want to mess up this 0 and 1 that is already there. 0 plus 1, 1. 1 plus negative 1, 0. 12 plus negative 1, 11. And then we have 0, 0, 1, 12. This is in row reduced echelon form. And we are finished with the row reduced echelon form of this augmented matrix. This translates into x, no y, no z equals 10. No x, 1y, no z equals 11. 1y equals 11. No x, no y, 1z equals 12. And there we have the solution. Okay. Make sure to practice this row reducing of matrices. And it is called, the whole thing is called the Gauss-Jordan elimination. We're skipping just the Gauss elimination because for a little more effort, we get to the row reduced echelon form as opposed to the row echelon form without being totally reduced. Let's do another example. Okay, so this one is going to be, I think, way more difficult. Example 3. Now, if you find yourself spending half an hour on one problem, you're not doing badly. It's okay, especially if we make mistakes, because then we have to go back and fix them. Yeah, some people, in some math courses, they come, they're doing their homework and they tell me, Mr. Saldivar, I spent half an hour in one problem. And I'm thinking, but did you understand it? Did it work for you? And say, yeah, it just took me a long time. Well, welcome to the club. It takes me a long time to do many problems. So that's the normal I guess that is what I'm trying to say. It is just a normal process. Okay, so example 3, we have 2x plus 5y plus 3z equal to -1, 4x plus 7y plus 2z equals 10. I can tell from this equation that at least one of the x, y, or z has to be negative because we're just adding positive coefficients multiplying with the variables. So there's no way we can get -1 unless at least one of those three variables is a negative number. Here, just by looking at this, we don't know. And then 6x plus 9y plus 4z equals -6. Again, that tells us, because all of those are positive coefficients, at least one of the variables has to be negative. Now, I don't know if it will be -6 or not. We don't know what the answers are. If there's even an answer, we don't know. So at first, we have to have an open mind. We don't know whether we have an answer or not. So what is the augmented matrix corresponding to the system? Matrix. Now, the matrix without being augmented means without this column, without the constants. So without, if we just call for the matrix of the system, matrix of the system, it would be 2, 5, 3, 4, 7, 2, 6, 9, 4. So just this 3 by 3 matrix would be the matrix of the system. But the augmented matrix means we're going to have -1, 10, -6 as an extra column. So now we got to start working with this. We don't have to deal with x, y, and z. It is implicit that this is the column of the x's, column of the y's, column of the z's, column of the constants. And now we go ahead and start working this out. And there is a very, very systematic way of doing this. First, convert this into a 1. Wipe those 2, wipe them off, and that means convert them into zeros. Next, whatever this number, convert it into 1 and wipe those 2, make them zeros. Next, convert this one into a 1, wipe those 2 off, convert them into zeros, and then we have a nice row reduced echelon form. Okay, converting this into a 1. So hang on, that should take one step, a second step with two parts to it. So putting a 1 and zeros here should take 2 steps. One for the 1, another step for the zeros. So that's 2 steps. A 1 here, step 3. Zeros, step 4. A 1 here, step 5. Zeros, step 6. So doing the whole thing should take only 6 steps. 1 zeros, 1 zeros, 1 zeros. And we go from left to right because we don't want to mess up what we already built early on. Yeah. Yeah. In construction, that happens when sometimes it isn't that it isn't well planned, it is just the way it is. Sometimes they build the frame of a house and then they have to put in the tub, but the tub doesn't go through the frame of the door. So they have to sometimes, you know, when they're still building the house, they might have to, take some, widen the entry to put the tub in there. I don't know. It's, you know, we want to plan things well because we don't want to mess something up that we already worked on and is looking good. And that's why we go from left to right. By doing that, we're putting zeros strategically so those zeros don't mess up the numbers we already have. Okay, so turn that into a 1, step 1. And remember, there's going to be 6 steps. We're going to do that simply by dividing by 2. So take the first row and multiply it by a half. Now, we're going to deal with fractions. Well, that's going to be just too bad. It is a little unfortunate, but oh well. As some teachers would say, you know, if I make a drama of that, they would say, take the drama to, you know, to somebody, not to me. Anyway, okay, so we got a 1 there. Step 1 is completed. Unfortunately, there's fractions, and it's not a big, necessarily a big, huge deal. It's just that we got to be very careful with the fractions. It's easier to make mistakes, in my opinion, when we have fractions. So let's get rid of this 4. Row 2 minus 4 times row 1. So multiply this by 4 and do 4 minus 4. And that's going to give us 0. Okay, here's where it gets difficult. 7 minus 4 times that. Actually, that isn't too bad now that I think of it. 7 minus, well, how much is 4 times that? Well, that's 20 divided by 2 is 10. So 7 minus 10, 7. Oh, wait a minute. This is, I'm sorry, we're on the second row, not the first row. So that should be 0. Please ignore that. So 4 minus 4 is 0. 7 minus 10 is negative 3. Yeah, when I put this 0 there, and I'm, you know, I got a little confused because I thought, wait a minute, we're supposed to have a 1. I'm going to write down the first row after we finish the second row. So 7 minus 10, 2 minus 6, 10 plus 2. Okay, let me double check. 7 minus 10 because we're multiplying by 4. 2 minus 6 because we're multiplying by 4. 10 plus 2 because we're multiplying by 4 and we're subtracting. Okay, the first row stays as is, 5 over 2, 3 over 2, negative half. The last row, we're going to do R3 minus 6 times R1. Now, how much do we need to subtract from the 6? So this one becomes 0. Well, 6, and we already have a 1, so 6 minus 6 is 0. So we're going to multiply by 6 this time. 6 times 5 is 30, divided by 2 is 15. So 9 minus 15 is negative 6. Multiply by 6, so that is 9, because 6 times 3, 18, divided by 2, 9. So 4 minus 9, negative 5. And then negative 6 plus 3, when we multiply by 6, negative 6 plus 3 is negative 3. Okay. Whoa. So the first column, beautiful. It is done. Now we focus on getting a 1 here. Okay. So we want to go diagonally, move, getting the 1s, and then up and down getting 0s. Diagonally getting a 1, up and down getting 0s. Well, there's no down after this one. Okay. So let's multiply the second row by negative 1/3, row 2. All right. 1, 5 over 2, 3 over 2, negative 1/2, 0, 1, 2/3, because we're multiplying by negative 1/3, negative 4. 0, negative 6, negative 5, negative 3. Okay, so we got 1. Let me start all over. We start with a 1 there, 0, 0. So this is the first thing we focus on, and then 0, 0. Then we move down to this position. Yeah, this one is already done. This position is 1, and now we're going to use this one to get rid of those two, the top and below the 1. Okay, so we will take the first row and subtract 5/2 the second row. Okay, so 1 minus 5/2 of that, still 1. And that's the beauty of going from left to right with zeros there. This one is not going to be messed up. This is kind of like getting your hairdo done. And then you already showered, so when you change to your, to your clothes, then your hair is still going to look great. Yeah. So 5/2 minus 5/2 of this guy is going to be 0. 3/2, whoa, minus 5/2 of that. Okay, that is complicated. I need a piece of paper, scrap paper, to do that, because that sometimes some of those computations are not as easy. So we have 2/3, and we're going to subtract. Here we are. We're going to subtract 5/2 of. So 2/3. We're going to subtract 5/2 of 3/2. Let me see that a little more closely. So 3/2, and we're going to take away 5/2. So 1 minus 5/2, 2/3 minus 5/2 of 3/2. Yeah, that's what it is. So that's why I'm going to do this on the side, because this computation is not necessarily obvious. 2/3 minus 15/4. Okay, we want to combine those two, so we need to multiply this guy by 4, so that is 8/12 minus, and we multiply this guy by 3, so that is 45/12. 2/3 minus 5/2 times 3/2. I'm just double checking. Okay. So that is going to be negative 30 something, 37/12. All right, so all of that to put down negative 37/12. Okay. And then negative 4. Yeah, the second row. Wait a minute. Sorry to do this. 1 minus 0, 5 minus 1. I think I did this computation wrong. Let me start all over. Sorry about that. Man, it's embarrassing to do this in the video. 1. 1 minus 5/2 of 0 is 1. 5/2 minus 5/2 of 1 is 0. Yes. 3/2. Yeah, I did this wrong. 3/2. 3/2, because we're doing row 1 minus something with the row 2. So 3/2 minus 5/2 of 2/3. Yeah, the 37, this number didn't look that good. But this I think makes more sense. 3/2 minus, simplify the 2, so we have 5/3. We still have to do common denominator, so multiply this by 3/3. So that is 9/6 minus, multiply that by 2/2, 10/6, and that is negative 1/6. That makes more sense. negative 1 over 6, and then negative 1/2 minus. So at this point, what I do is use scrap paper to do my little computations. Negative 1/2 minus 5/2 of negative 4. So that is negative half. Double negative is plus. 20 divided by 2 is 10. 20 divided by 2 is 10 plus, so that is 10 minus a half, that is 9.5. Or the same thing as 9 times 2, 18 plus 1, 19. So this is the same thing as 19 over 2, positive. Second row, 0, 1, 2/3, negative 4. Third row, 0, negative 6, negative 5. Oh, wait a minute. Whoops. I wanted to have a 0 here. So I'm just going to finish copying this down. I should have done 2 elementary row operations, one to get the 0 here, another one to get the 0 there. So, but it's okay. We can do that next. Instead of doing 2 elementary row operations in one step, now I'm going to do 2 elementary row operations in 2 steps. So I want to get rid of this 6, negative 6, by adding 6 times this onto here. So row 3 plus 6 times row 2. The first 2 rows are going to stay the way they are. 1, 0, negative 1 over 6, 19 over 2. 0, 1, 2/3, negative 4. Now we're going to do this. 0 plus 6 zeros, still 0. Negative 6 plus 6 ones, 0. Negative 5 plus 6 of those. Well, 6 times this is 4. 6 times 2 is 12, divided by 3 is 4. So negative 5 plus 4 is negative 1. Negative 3 plus 4 of those. That's going to be a big number. 6 times negative 4 is negative 24. So negative 3 plus negative 24 is negative 27. I think I made a mistake, but let's continue with this. We can try to fix the mistake in a little bit. So there's our matrix. So far we got 1, 0, 0, 1, 0, 0. Now we want to change this into a 1 and then 0, 0. And then we're going to have our solution, a nice, neat, clean solution. Although I have a feeling I made a mistake at this point, but I think I want to finish it and then look for the mistake. So change that into a 1, that's easy. Multiply negative 1 times row 3. 1, 0, negative 1 over 6, 19 over 2, 0, 1, 2/3, negative 4, 0, 0, 1, 27. Yes. Okay. Now we want to wipe those 2 off. So we have a nice diagonal of 1s, 0s either below or above and below or above of the 1s. So how do we get rid of that guy? Row 1 plus 1/6 of row 3. So 1 plus 1/6 of that. See, that's why the 1 does not get affected, because there's a 0 here. 0 plus 1/6 of that. That doesn't change. We're good. Negative 1/6 plus 1/6 of 1, well, that's 0. 19/2 plus 1/6 of that. That is a little more work. So I'm going to do that here. 19/2 plus 1/6 of 27. Well, that simplifies. That is the same thing as 19/2 plus 27 over 6, but that simplifies down to 19/2. We can divide by 3 on the numerator and denominator, and we have 9 over 2, and that is 28/2, which is equal to 14. So this guy is 14, according to this. Then we do R2 minus 2/3 R3. See, the advantage of having 1 is that you don't have to think too hard what to subtract, how much to multiply this to then subtract to get a 0 there, because all you have to do is multiply by 2/3. Since we already started with a 1, multiply by 2/3, we get 2/3, subtract 2/3 minus 2/3, and there we have it. So 0 minus 2/3 of 0, 0. 1 minus 2/3 of 0, 1. 2/3 minus 2/3 of 1, 0. Negative 4 minus 2/3 of that. Negative 4 minus 2/3 of 27. Well, that is negative 4 minus 54 over 3, and that is 18. Negative 4 equals negative 4 minus 18, and that is negative 22. Zero, 0, 1, 27. So it appears, if I didn't make any mistake along the way, it appears that x, no y, no z equals 14, y, no x, 1y, no z equals negative 22, no x, no y, 1z equals 27. Before I box it, I really want to double check that the answer is correct. So I'm going to come back to the original problem. Okay, 2x plus 5y, 2x plus 5y plus 3z should be equal to negative 1. Well, let's see if it is so. I'm not going to put equal to negative 1 yet, because I'm going to plug in the 14, the negative 22, and the 27 and see if we actually get negative 1. I'm a little doubtful. So, okay, so that, if we plug those numbers in for x, y, and z respectively, we get 28 minus 22 times 5 is 110, plus 27 times 3 is 81. So that is, those added together, the positive numbers added together, that's 109 minus 110. And sure enough, that is negative 1, as it's supposed to be, because in the original system of equations, we have 2x plus 5y plus 3z should be negative 1. Okay, so the first equation checks. Let's see if the second equation does. 4x plus 7y plus 2z equals 10. Well, let's see if, no, I'm not going to say it is equal to 10 yet. I don't know that. It should be equal to 10, but let's see. 14 times 4, 56. 7 times negative 22. Well, 7 times 2 is 14, carry 1. 7 times 2 again is 14, 15, plus 2z, 54. Let me double check the 22 times 7. No, this calculator is going to be better. 22 times 7. Yeah, 154. Because I think this is not going to work. Those two together, and let me check. 4 times 14. 4 times 14. 56, yep. And then 2 times 27, that's 54, I'm pretty sure of that. And let me double check the second equation. Second equation is 4x's, 7y's, and 2z's. Yep. Because then we end up with 110 when we add the positive numbers, minus 154 is equal to negative 44. But that's a bad thing because we're supposed to end up with 10, not 44. Well, negative 44. So though those solutions are incorrect. Yeah, they satisfy the first equation, but they don't satisfy the second equation, and we do not know whether they satisfy the third equation. As soon as they don't satisfy one of the equations, it doesn't matter which one, that means that the solution is wrong. So if I don't find it very quickly, I may ask you to find the mistake. First, the first thing to check is whether the coefficients were written correctly. 2, 5, 3, negative 1, 4, 7, 2, 10, 6, 9, 4, negative 6. And then we're going to label the steps. So this is step 0, step 1, step 2, step 3, step 4, step 5, step 6. Usually it takes only 6 steps, but remember I forgot to get rid of this negative 6. So we did that in a following step. And that's why this problem took 7 steps. Typically a problem like this takes about 6 steps, not 7. 5, 3 over 2, negative 1/2. Yeah, I have to check the other ones. So as part of the homework for this video, please find mistake. It doesn't work because the numbers don't work, because when we plug into the second equation of the original system of equations, we don't end up with 10. We're supposed to end up with 10. So please find the mistake. And by that we mean step where that happened. Fix it and tell the correct answer. Yeah. I don't want to take up too much of the recording or the time to review the steps. I could pause it, and in fact, I have done that in the past. I pause it, but I think it's a good thing for students to go over this on their own and see where the mistake is. That incidentally makes a good problem. All right. So let me just recap very, very quickly. we're not focused only on trying to solve a system of equations. We're focusing on reducing a matrix into row reduced echelon form by using the three row operations, the three elementary row operations. So our goal is not just to get a solution. Our goal is to obtain this setup, this format, which is what we call row reduced echelon form. All right, guys, we will stop the video here.